So in Chapter 4, we're going to talk about securing Layer 2 protocols. This is two primary protocols that are highly susceptible to attack. One is Arp, the Address Resolution Protocol, and the other is Spanning Tree, the Spanning Tree Protocol. Both protocols, well, we can't really live without them. They both have to exist. You can try to design them out of the network as much as possible by shrinking the size of your broadcast domains or by doing routing all the way to the edge of your network, but in the end, you still need these protocols to run in the network. What we're also going to talk about in this chapter is something called Dhcp Snooping. Although it's not a Layer 2 protocol, Dhcp is actually a Layer 3 protocol. Actually, technically, it's an application layer protocol, but it allows us to resolve IP addresses or to assign IP addresses and IP information to clients. We still classify it in this category because of how Dhcp snooping works and how it's affected on the network from a Layer 2 perspective. So we'll talk about these protocols, but the first one we're going to take a look at is the Spanning Tree Protocol. Okay, the Spanning Tree Protocol. Now, the Spanning Tree Protocol is a very, very important protocol in the function of any Layer 2 network because it allows us to have redundant network connections without having the deleterious effects of these redundant connections. For example, let's say that this is a pretty typical network design. I've got a couple of switches that are connected at the distribution layer, probably some sort of ether channel connection between those core switches, and then I have on my access layer redundant connections that go down or up to the distribution layer. Pretty typical design. This is what we built in GNS3 as well. So the distribution layer is providing our Layer 3 services. It's providing QoS, it's providing policies, etc. But at the access layer, we're providing all of our Layer 2 services. Clearly, you can understand why this particular type of design would be necessary, right? This type of design would be necessary because if one of these distribution layer switches were to fail, we could still function by using the other distribution layer in the network. But what is the negative effect of having this type of topology in a Layer 2 design? Loops, switching loops, right? We create loops. So if there's a client down here and that client sends an Arp request, for example, which is a broadcast, that Arp request is going to be duplicated out of every port except for the port it came in on because it is a broadcast. This switch is then going to forward that Arp request on to the other switches in the network because it's a broadcast except for the port that it came in on. This switch then in turn would send it up to that switch. This switch would send it down to that switch, and basically this traffic would loop around the network indefinitely. And because Layer 2 frames don't have a time to live like a packet does, these frames would essentially loop the network indefinitely until the traffic became so, increasingly so bad that the switch or the networks would just stop responding. We would end up, creating something called the broadcast storm. So we still want to have the ability to have that topology. That topology is still very important to us. We want to be able to have all these redundant connections in the topology, but I don't want to have all the negative effects of having these loops in the network. So we run the Spanning Tree Protocol, and even though it's a little bit beyond the scope of this class to define specifically how the Spanning Tree Protocol operates, but we will just say, I'm not going to get into the specifics of Spanning Tree, but we'll say that there's an election process that occurs where a root bridge gets elected. Once that root bridge is elected, we then go through the process of identifying root ports. Then we go through a process of identifying designated ports. But eventually what will happen is that one of these, or multiple links in this particular topology, will essentially be disabled, for lack of a better term. So let's say, for example, this guy over here on the left becomes the root. Dang it. Oh, I have to draw it all over again. All right. Try that again. So let's say this switch on the left becomes the root based on the election process, which I will demonstrate to you guys. Even though we're not going to go through the specifics of the election process, if this switch here becomes the root, then this path here might become a primary path, this might become a primary path, and these three links here might become a primary path. But these links here on the right side will be temporarily disabled. Those links will be temporarily disabled to get rid of the loops in the topology. Okay? If you guys have questions specifically about how the spanning tree protocol works, that's no problem. I'd be more than happy to go through it. It's just a little bit beyond the scope of what we're talking about today. Right? I will show you guys how we can control spanning tree and how we can ensure that a particular bridge becomes the root for a particular VLAN. And then I will also describe how we can verify the operation of spanning tree in our network. But I just don't want to go into the specifics of the algorithm and how Bpdus get exchanged every 2 seconds on every interface, and how the switches use something called a bridge ID to identify who the root is, et cetera, et cetera. That's all stuff that you would have learned as part of your discussion in CCNA. All right? But there are, because spanning tree is a necessary protocol in our topology, and because spanning tree is an automatic protocol, meaning that it exchanges everything automatically, there is a concern as to whether or not spanning tree is vulnerable to attack or somehow otherwise manipulating spanning tree. So that's one of the things that we need to consider as part of this process, is how do we protect spanning tree, and what are some of the best practice standards that we use to configure spanning tree. How many of you are familiar with how spanning tree works, the algorithm, the election process, and so on? Since the last time you took my class, you would have learned it. Yes, absolutely. If you're not completely familiar, go onto the YouTube channel and take a look at the spanning tree video, the spanning tree chapter. It'll walk you through all that stuff. But you're not going to be tested on that in this class. You will be tested on the protection mechanisms, so we're going to talk about those. All right? One of the tools that's part of the spanning tree toolkit is called the Portfast feature. Now, this feature is not necessarily a security component. It doesn't really enhance our security posture, but it is certainly a best practice configuration, and it allows our host ports or our edge ports to start functioning without having to go through all of the different processes in spanning tree. There's a life cycle that spanning tree goes through when a port comes up initially. The port always starts in some sort of blocking state. Okay? Port always starts in a blocking state. You plug a computer in, it's going to start in a blocking state. And then because the port is in a blocking state, it's not forwarding frames for the clients themselves. All right? Now, what the switch is going to do is it's going to wait to see if it gets a Bpdu. Bpdus are frames that are generated by switches to disseminate information about the spanning tree topology. Well, PCs don't generate Bpdus. They just sit there and act like computers. So they're not necessarily generating Bpdus, but they do want to send information across the switch port. The problem is the switch doesn't know what decision to make because it's not getting Bpdus from the PC. It doesn't know what decision to make when trying to identify what the status of that port should be. Ultimately, what are the two final decisions that a switch can make with regard to a particular port? Is it going to be in the blank state or the blank state? Little Mad Libs, right? You can put whatever you want in there. Ultimately, what's the goal? Do I put the port in a blank state or a blank state? Blocking or forwarding, exactly. That's ultimately the goal of spanning tree. Is the port going to be blocking permanently or is it going to be forwarding permanently, right? Well, in order to determine that, the Bpdus have to be sent and received. The problem is that the Bpdus don't come from the PC, so there's 20 seconds, it's called a max age timer, that the switch port just sits there and says, somebody just plugged in, I don't know what to do, I'm not getting Bpdus. So for 20 seconds, that port stays in a blocking state. Then it transitions over, depending on the version of spanning tree, transitions over to the listening state. Now, the listening state is also a blocking state, so we're still not forwarding frames in this particular state, but now the switch is still kind of sitting there waiting. Am I going to get Bpdus? Am I going to get Bpdus? I would not see this particular state here if I had plugged another switch in, because as soon as I get a Bpdu on the port, I go into this listening state. So this listening state is another 15 seconds where I'm not forwarding frames across the interface. I'm not allowing data frames to go in and out of the interface. All I'm allowing are Bpdus to come in. And then the switch might decide to go over to, well, it will decide actually, to go over to the learning state. That's also a 15-second window. So now the switch is in a learning state. The difference between the listening state and the learning state is what? Any ideas?
Learns MAC addresses learned on them from the Bpdus or from the port.
From the port, right. The difference between listening and learning is if frames, regular data frames are coming into the port. In this particular case, I'm updating my MAC table. I'm still not forwarding frames. I'm still not allowing frames to go in and out of the port. But if I do receive frames, I will update my CAM table with the appropriate MAC address information. And then finally, the port will either decide to transition back to the blocking state if it decides that this port is going to cause a loop, or it might transition into the forwarding state if that's supposed to be a FWD, if it determines that that port is not going to cause a loop. These are kind of the different states that we go through in spanning tree. If it's rapid spanning tree, there's no listening state, but there's still 20, 35 seconds of blocking. If it's a regular spanning tree, 802.1d or PBST+, you're talking about 20, 35, 50 seconds before a port actually is available for a client to use. Within that 50 seconds, DHCP has failed because the client sees the link status is up. So the client's just going to start sending its DHCP discover messages over the port. DHCP could have failed at this point, and so on. So on our edge ports, on our host ports, we don't really want to have to go through this whole process of identifying whether or not the port is going to cause a loop and so on. The reason we're talking about this, obviously, is because of this Portfast feature. The Portfast feature gives us the ability to place, bless you, to place a port into the forwarding state immediately upon link detection. All right, so what happens? Well, how do I configure this? There's two ways to configure Portfast. You guys use Portfast in your network? Yep. It's not really necessary. I wouldn't say that it's necessary for a switch to function, but it does enhance the services that the switch needs to service clients. One of the options you have is to do Portfast default, where you're actually going into global configuration mode and you're enabling Portfast on the entire switch. I think somebody went out with it, because I put it back up there when I came back. Yeah, but I think she put the stopper in the door anyway, so. All right. When I configure spanning tree Portfast default, does anybody have any idea what ports that affects? All of them except trunk ports. Spanning tree Portfast default only works on host ports. It does not enable spanning tree on trunk ports. Now, so that means any access port on your switch at this point will now be running Portfast, except for trunk ports. Does this disable spanning tree on the interface? It does not. It allows the ports to go immediately into a forwarding state once a link is detected, but if a Bpdu is received on a Portfast port, what happens to that port? Negative. On a Portfast port, if a Bpdu is received, the port simply reverts back to a normal spanning tree port. It goes back immediately into the blocking state, so it does technically turn it off, but then it just kind of tries to transition through all of those different states again. So Portfast default does not cause ports to error disable. It just simply reverts them back to a regular spanning tree port if they receive a Bpdu. Now you may have to, or you may decide that you don't want to enable spanning tree globally. Actually, I prefer the global option. But you may decide that you want to simply enable it on a per interface basis. So there is the interface specific command. Go into the physical interface and just simply type spanning tree portfast. If this is an access port and it's not receiving Bpdus, same thing. It'll immediately start forwarding frames. As soon as it receives a Bpdu, as soon as this port receives a Bpdu, then it will lose its portfast status and it will revert back to a normal spanning tree port. All right? In fact, it even says here, it says, portfast has been configured on Fast Ethernet 01, but will only have this effect when the interface is non-trunking. Okay? Important point to note. By doing spanning tree portfast default, or even by enabling portfast explicitly on a port, the portfast feature is only enabled if the port is not a trunk. What if I do want to enable a portfast port as a trunk port as a portfast port? Is there any reason why I would ever want to configure a trunk port to use portfast? VMware servers, exactly. Router on a stick, VMware server, those kinds of situations. I would want to enable portfast as a trunk because, and you have to explicitly mention it because otherwise portfast won't run on that interface. So there are instances where you'd want to go into the switch port and enable the portfast trunk command. If it's a trunk port that goes to a VMware server, a trunk port that goes to a router on a stick, you certainly would never want to do this on a port that goes to another switch or any port that's going to receive a Bpdu. All right? It does mention here, hey, you should only enable this on ports that have a host connected. That's a little bit misleading because a VMware server could house multiple hosts, but that's kind of the general point. Don't enable this on a trunk port that goes to another neighbor, another switch. What about a what? A phone would be okay. Because even though a phone does act as a switch, it doesn't send out Bpdus. It doesn't participate in the spanning tree domain. So that's a good question. A phone would definitely be okay. All right. So I've gone ahead and added this to our document here. I'd already done this previously as a best practice standard. Going to do spanning tree. Oops, that's the Bpdu guard one. I meant the global one. Here's our global mode. Spanning tree portfast default. Enable spanning tree on all of my non-trunking ports. We'll talk about Bpdu guard in a second. On trunk ports, you may want to implement spanning tree portfast trunk. Only enable this on ports that go to that are connected to a VMware server, router on a stick, etc. Okay? There are some commands that you can use to find out what ports are portfast ports. If I say, for example, come into my switch here, and I go into my global configuration mode, and I type spanning tree portfast default. All right. Show spanning tree portfast. I should be able to see show interface. Let me see what the command is. It's show portfast interface. No. There is a command to see which one is running portfast. Might not be available in this. Nope, that's a different feature. I mean, we can see if portfast is enabled by doing a summary, but what I was trying to show you, there is a command, I've seen it before, maybe it's not in this iOS. There is a command where you can actually view which ports are actually operating in portfast mode. But we can see here the Portfast default option is enabled globally. If I do a show spanning tree summary, that will tell me whether or not Portfast is enabled globally. But there was a command to see, and I can't remember which one it is. I thought it was show port interface Portfast or show Portfast interface, but I guess not. Yeah, we don't have it. Anyway, there is a command. I'll have to look it up later for you guys. But in any event, do you know where we want to enable Portfast? We want to enable Portfast on all our edge ports. Do you guys use the global option typically, or do you guys use the interface option typically? Interface? Yeah. That's fine. It just requires you enable the command on each interface. But the nice thing about using the interface option as opposed to the global option, there are instances where you may actually have switches connected that are on access ports. They're not on trunk ports. Where you have a switch that's aggregating a bunch of hosts on a particular VLAN, and that port happens to be an access port, well, Portfast is not going to work very well on that port. It's not very common, but you could have it. All right. Some of the other things that we have to concern ourselves with regard to spanning tree, primarily is spanning tree topology attacks, where I'm trying to either insert myself as the root of the domain, or I'm trying to otherwise affect the topology and what the topology looks like. Here's an example. The root bridge is elected based on priority and MAC address. This is a piece of data that gets transmitted within the Bpdu, and the lowest value wins. So if one switch is advertising a priority of 8192, and another switch is advertising a priority of 4096, the switch with the lowest priority is going to become the root. Okay? Well, let's say, for example, in my normal topology, maybe this is not a PC, but it's a switch or whatever. This is before this guy sending in these Bpdus. So we'll redact that there. So this guy's connected to the network. Well, he's either not sending Bpdus or he's sending inferior Bpdus. So he's not going to be elected as the root, which means this becomes a designated port. That becomes a root port. The F in this case stands for forwarding. That becomes a designated port. That becomes a root port, and so on. Okay? And all the traffic that's flowing between the switches flows in this direction, in the east-west direction, as opposed to the north-south direction. So all the traffic is flowing between the switches over this link, and this guy down here who wants to see all that traffic is not seeing any of that traffic. But if I could somehow open up an application and start generating superior Bpdus, because Bpdus are not authenticated. There's no way to configure authentication for spanning tree. So Bpdus can just be sent out gratuitously, and the other switches will receive those Bpdus and they will accept whatever value they see in that domain. So if this guy sends out Bpdus that are superior, the priority is 0, which is the lowest possible priority you can have. Guess what's going to happen? The switches are going to think that that guy becomes the root of the network, and then instead of the traffic flowing across this link, the root ports become these ports, and all of the traffic flows downstream to the client that's connected and sending in the superior Bpdus. You can see where there's a huge benefit here, at least from an attacker's perspective, because all the traffic going from the switch on the left to the switch on the right is going to go through the attacker's machine, and I can now capture all that data and start looking at information in the network. Inherently, spanning tree is susceptible to this type of attack because, like I said, spanning tree doesn't have any protection mechanisms built into it, at least from an authentication and security standpoint, right? You can't enable, you cannot enable things like authentication. There's no hashing process. So spanning tree will listen and it will just believe what it hears. Well, there must be a way to protect ourselves in this case then, right? You would hope. Of course there is. That's why we're talking about it. there is a feature called Bpdu guard. Bpdu guard, which is also a best practice configuration, is a feature that you typically enable on a per port basis or a global basis, but it's supposed to be enabled on your host ports. And essentially what Bpdu guard does is as soon as a port receives a Bpdu that has this feature enabled, the port error disables. Port shuts down. Okay, it's probably the one that you guys were thinking of before. So there's two ways to implement Bpdu guard. You can either implement it globally, or you can implement it on a per interface basis. So let's say, for example, I wanted to configure it globally. I would go config t, spanning tree portfast Bpdu guard enable. Default, sorry. All right, enables on the interface. Spanning tree portfast Bpdu guard default. Now actually, Bpdu guard doesn't really have anything technically to do with portfast. They're completely separate features, but what you're saying in this case is go ahead and enable Bpdu guard on all of my ports that have portfast enabled. That's why you see the two words tied together in this particular command. So Bpdu guard in this case will be enabled on all of my portfast ports, which ends up being all my host ports, doesn't it? That's one option that you have. Or you could go into the interface specifically, interface Ethernet 3.1, and you can say spanning tree Bpdu guard, not filter, you don't want that one, enable. This explicitly enables Bpdu guard on the interface. Whether it's portfast or not, that enables Bpdu guard on an interface. Okay? Do you guys use this feature? Don't know? Yes? No? It is a pretty standard feature that you're supposed to implement when you implement your layer 2 network. Enabling it globally for your portfast ports, that's probably one of the best options. But again, if you guys are focusing on putting all of your best practice standard configs on the interface, then you can enable it explicitly on an interface. You would have to do this anyway on a trunk port. Like a trunk port that goes to a VMware server or a trunk port that goes to a router on a stick, you would have to enable Bpdu guard on that interface unless you've enabled the portfast trunk config on that interface as well. All right, so if I do a show spanning tree summary, I can see now that portfast default is enabled and Bpdu guard default is enabled. By the way, what is extended system ID? Since it's already on the screen here, what is extended system ID? Anybody have any idea? It is obviously related to spanning tree. You guys remember from our discussion back in CCNA days? Cisco runs a different version of spanning tree than everybody else. They run per Vlan spanning tree. It's called PVST Plus or RPVST Plus for rapid. So Cisco runs per Vlan spanning tree, which means they use a different bridge ID format. Instead of having a 2-byte priority and a 6-byte MAC address, they have a 4-bit priority, a 12-bit extended system ID, and a 6-byte MAC address. That 12-bit extended system ID field is used for VLAN, to identify the VLAN. So we can run spanning tree per VLAN in that instance. All right? I just thought I'd ask just to see if you guys remember that stuff. But you can see that there are several other features that are also available. Things like filter, which you should never use, loop guard, uplink fast, backbone fast. Backbone fast and uplink fast should not be necessary. The only time you'd ever run backbone fast and uplink fast is if you're running the slow version of spanning tree. But we don't run the slow version of spanning tree, right? We run rapid spanning tree. 802.1W or RPVST Plus if you're looking at Cisco's version. So those are kind of deprecated features in spanning tree. We will talk about we won't really talk about filter. Bpdu filter basically essentially disables Bpdus from going out of an interface and coming into an interface. You should probably never use that, but
correct me if I'm wrong, rapid spanning tree is backwards compatible, correct?
it is. It is. All versions of spanning tree are compatible with each other because they all use the same essential algorithm, the 4-step process to building the topology. Elect the root bridge. On all the non-root bridges, pick your root port based on the path cost to the root, which is a cumulative path cost to the root. 10 meg costs 100 meg costs 19, 1 gig costs 4, 10 gig costs 2. Once we've elected our root ports on our non-root bridges, then we elect our designated ports on all the segments. The designated port is the interface that connects to the switch with the lowest bridge ID for that shared segment. And then the last step is all the ports are blocking. All the remaining ports are blocking. Well, all of the algorithms use the same method. I mean, all of the versions of spanning tree use the same basic algorithm. All right, so again, best practice standard. All right, let's see, global mode. I guess I should put it in here. I didn't, certainly spanning tree Portfast Bpdu guard. There should be a default command after that. As long as you're also using Portfast default. And I did forget to put this in here. I think this is necessary as well. You're going to want to run spanning tree mode rapid PVST, right? So go to my switch here. That's what actually enables the spanning tree rapid option. Spanning tree mode rapid PVST. So that's what enables rapid spanning tree. As long as you do that on all your switches, you're going to be running really the most efficient, not the most efficient, but certainly there's one other spanning tree mode that's a little bit more efficient called MST, multiple spanning tree, but it still uses PVST as its base algorithm for base operations. Okay. So as a best practice standard, let's put enables per Vlan rapid spanning tree. All right, so globally you want to enable Portfast Bpdu guard default. Spanning tree Portfast Bpdu guard default. All right, so we've already seen several different commands that we'd run as kind of a best practice standard. Spanning tree Portfast default, spanning tree mode rapid, spanning tree Portfast Bpdu guard default, spanning tree extended system IDs there by default anyway. Cisco always uses an extended system ID unless you turn it off. And then Bpdu guard enable could be enabled on a per interface basis.
If you want to turn the extended system ID off on your another layer 2 device is not Cisco, that when you want to disable, or it doesn't matter?
It doesn't matter because the way that Cisco split that field up, it's still backwards compatible with the older version of the bridge ID format. So you don't necessarily need to change it. All right. Let's see, host ports, spanning tree Bpdu guard enable. You can enable on a per interface basis for non-Portfast ports. You would not have to do that in conjunction with what you're doing in global mode. If you've enabled it on global mode, as long as the port is a Portfast port, you're good to go. All right. And then on our trunk ports, we may decide to run spanning tree Portfast trunk. And we'll talk about root guard in a second. By the way, the spanning tree Portfast default will work with trunk ports that have, the spanning tree Portfast Bpdu guard default will work with ports that have Portfast explicitly enabled on a trunk. As long as the port is a Portfast port, Bpdu guard will be enabled on that port. Again, there's no reason why, say for example, a VMware server should be ever sending Bpdus. There's no reason why a router on a stick should ever be sending Bpdus. So that is a good command to run on those types of ports. Would you ever enable Bpdu guard, say, on links like that? No. Links that go to other switches, you definitely would not want to run Bpdu guard on because those ports are disabled. By the way, you can configure also an error disable recovery cause for the Bpdu guard feature, which may be something that you actually decide you want to do. Let's say, for example, I've decided to enable Bpdu guard on my switch. I can do an error disable recovery cause Bpdu guard. So just like we did this with port security, if for some reason an interface error disables because it received a Bpdu, this error disable recovery cause will allow that port to auto recover itself in the event that the Bpdu stop on that interface. Which, by the way, I would kind of recommend, right? You don't want all your ports shutting down just because somebody could launch a denial of service attack on your network just by moving a switch around and plugging it in to cause Bpdus to be generated. All right? Maybe if that is happening, though, you'd still want to find out, obviously.
Yeah, it still does logging, right? So
It will still log, yes.
when it trips, it still logs.
Yep, it will generate a syslog message. So let's say, for example, interface Ethernet 3.1, spanning tree, Portfast, and then I'll do a spanning tree Bpdu guard enable. So port 3.1, and now if I go to my topology and I plug something into port 3.1 to generate a Bpdu, you will see that it does generate a message, right? Spanning tree blocked because of a Bpdu guard, received a Bpdu on port 1 with Bpdu guard enabled. I'm disabling the port, puts that port in an error disabled state, the status goes down. Now, remember, I set my error disable recovery time to 30 seconds, so if I do delete this line here, those Bpdus should stop, and because I did enable the error disable recovery cause of Bpdu guard, I should see in a couple of seconds here that the port re-enables itself because it's no longer receiving Bpdus on that interface. All right. We missed the recovery last time because I wasn't paying attention, but we'll see if it pops up this time. There we go. Attempting to recover from Bpdu guard error disabled state. This port went to up because there were no Bpdus being received on the interface. Okay. If you're not running this feature, certainly something to look at. This is what I just demonstrated, the ability for us to establish a recovery time to auto-recover a port that goes into an error-disabled state because of a Bpdu. So the first command there, spanning tree Portfast Bpdu guard, enables, actually that's not the correct syntax there, or at least the prompt is not correct. That's an interface-specific command. But all we're doing is enabling Bpdu guard on an interface. And then error disable recovery cause Bpdu guard. In this particular case, we set the recovery interval to 400 seconds. 400 seconds. Another potential vulnerability in spanning tree is the attempt of somebody trying to claim to be the root. If you've got a topology like our topology right here, you've got a topology like this. This switch here is the root. This switch is the root for, say, VLAN 10. This switch is the root for VLAN 20. And then they back each other up. So this guy might be the backup for VLAN 10. This guy might be the backup for VLAN 20. But you definitely want your distribution layer switches acting as the root for their respective VLANs. The thing is, somebody might plug a PC in to try and simulate that they're going to become a root, or somebody might misconfigure this access layer switch to become the root just by simply programming a lower bridge ID. They just set a lower priority on the switch, and all of a sudden, your access layer switch becomes the root. So there is a feature that we can enable called root guard, and you would enable this on your downstream links. Change my pin color here. You would enable this on your downstream links so that if I do receive any superior BPDUs on these links, those links go into something called an inconsistent port state. They stop forwarding frames. They basically block. The switch is saying, somebody's claiming to be the root on this link. I know that there's nobody down there that should be the root, so I'm going to go ahead and block those ports. Let me show you what that looks like. I go into my distribution layer switches, which is these guys here. I'm going to configure this on 2.0 and 2.1, which are my downlink ports to my access layer. So let's go into DSW1. If I have it open here, I don't think I actually have DSW1 open. Let's go ahead and open up DSW1. All right. First of all, I'm going to do a show spanning tree VLAN 10 just to see who's the root for VLAN 10, and I can see in this case that I'm the root for VLAN 10. And I'll do a show spanning tree VLAN 20 to see who's the root for VLAN 20. I'm the root for VLAN 20, but I also can tell that the priority hasn't really been modified. The only reason I'm the root is because I happen to have the lowest MAC address. So that's not a good config. I would like to set the priority lower than the default value to ensure that I'm going to become the root, and I'm not basing it on MAC address because MAC address is somewhat random depending on the age of the switch and so on. So I'm going to come in here, I'm going to say spanning tree VLAN 10, root primary, and I'll say spanning tree VLAN 10 or 20, root secondary. What that does is that sets the spanning tree value, that sets the priority for that particular VLAN to a lower value than the rest of the domain, so that I can always ensure that I'm going to be the root for that particular VLAN. Okay? That has nothing to do with root guard. All I was doing was setting the priority of the switch to make sure that this switch would become the root for that particular VLAN. Make sense? Now I'm going to enable the root guard feature. Config T, interface range Ethernet 20-1, spanning tree guard root. This command can only be enabled on a per interface basis. There is no global version of this particular command. So I've enabled root guard now on my two downlink ports. So this port and this port, I've enabled root guard. So I'm going to go and change the priority of this switch so that it starts claiming to be the root for that VLAN. You can see what will happen. Go into ASW1. Well, I would have to do it on ASW2 as well, because that's the other link, but let's go into ASW1 first. I can find the dang thing. Here we go. Config T, spanning tree VLAN 10, priority, and I'm just going to set the priority to 0. So lowest possible value. The only other thing that could trump this is a lower MAC address, but now I'm sending out superior BPDUs. ASW1 is telling all the other switches, my priority for this VLAN is 0, And because everybody's priority is higher than 0, that means ASW1 is essentially claiming to be the root for this particular VLAN. If I go back to my DSW1 switch, you will see the syslog message, spanning tree root guard block. Root guard is blocking port 20 on VLAN 10. All the other VLANs are allowed to work over that port, but VLAN 10 is being blocked because there's a downstream switch claiming to be the root for that particular VLAN.
So what does that do for DSW2, which you did not set root guard on?
Nothing.
So it is now thinking that its root is this ASW?
Correct. That's why you would also configure the same configuration on those downstream links as well. You want to make sure you're consistent across the board on your configuration. All right. So essentially, for VLAN 10, this interface for VLAN 10 is being blocked. This interface here. Now, if I went over here and I started sending out superior BPDUs there, that interface would get blocked. And if I had the root guard feature enabled here, those interfaces would be blocked as well for the respective VLAN. See, the root guard feature only affects clients in the VLAN that's claiming to be superior. So if this switch, because we set priority per VLAN, for example, if I go into ASW1, and I do a show spanning tree for VLAN 10, you can see that I have my priority at 0. But if I do a show spanning tree for VLAN 1, you can see my priority is the default because we set spanning tree priorities per VLAN. So because this switch is not claiming to be the root for VLAN 1, we're still allowing that VLAN 1 traffic to pass through those interfaces.
And 20 as well.
And 20 as well. Right.
Okay.
Right. We're only blocking the VLAN that's being affected by this. Now, if I go into DSW2 and I do a show spanning tree inconsistent ports, let me do the whole command. Show spanning tree inconsistent ports. I can see which ports are being blocked because of this current state of root inconsistent, meaning that there's somebody claiming to be the root. So it's not the same as error disabled because the port is technically not error disabled, right? Other VLANs can still pass through the interface. If the port was error disabled, then nobody would be able to communicate. All right? How do I fix this problem? Well, I go into ASW1 and I stop claiming to be the root. That's how I fix the problem. So I go into ASW1 and I say spanning tree VLAN 10, priority 32768. Just set it back to its default. And as soon as that happens, this switch here says, oh, you're not claiming to be the root anymore. Thanks for doing that. I appreciate it. I should have got a message. Yeah, that's right. I should have got a message indicating, there we go. Just took a little while. Root guard is unblocking the port on VLAN 10 because you're no longer claiming to be the root. So you can see why this would also be a best practice standard. Under distribution layer switches, enable the root guard feature so that you're protecting those switches from losing their status as the root. All right. There are other spanning tree protection methods, but for the most part, these are the ones that we use on a regular basis. Go away. There we go. Root guard, Portfast, Bpdu guard. Those are the three pillars of protection for spanning tree. Root guard, Bpdu guard, and Portfast. Okay. So the next protocol that we're going to talk about in this chapter, and as far as actually providing some sort of protection mechanisms to our domain, is we need to protect DHCP. DHCP, just like any other protocol, well, just like a lot of other protocols, is a very dynamic protocol in nature. It's a client-server protocol. The DHCP messages are broadcast or flooded throughout the domain, which means that there are two types of attacks that could exist in DHCP. What are the two most common types of attacks for DHCP? Spoofing, which would also result in man in the middle, right? Because you're spoofing a DHCP server for the purposes of either influencing the configuration of the DNS server or the gateway address. What would be the other type of attack that we'd be concerned about?
Denial of service by taking all the addresses?
Yep, denial of service by taking all the addresses. That's called the Dhcp Starvation Attack. Dhcp Starvation Attack. Somebody sends out a bunch of DHCP discover messages, spoofing a bunch of different MAC addresses, and all of a sudden there's no more addresses in the scope. You might think, well, wait a minute, wouldn't port security protect me from that? Because the way that DHCP does its bindings is it does its bindings based on MAC address, right? You guys agree with that? When a DHCP server sees a discover request, it looks at the MAC address and it maps that MAC address to an IP address and sends out a lease information. So in order to facilitate a DHCP starvation attack, wouldn't I basically have to just send out a bunch of frames for DHCP discover messages with different MAC addresses? Yeah. Wouldn't port security protect me from that? He's shaking his head no. You're shaking your head yes. So the people are like, I don't know. Would it? Would it not? You would think, right? Because in order for me to send out a whole bunch of DHCP discovers with different MAC addresses, I'd have to have a different source MAC on the port. But the reality is no. Why? Because if you look at a DHCP discover message, the frame information is in the DHCP payload. It's not the actual frame itself that the DHCP server looks at when it's doing the binding. All right, let me see if I can show you this without, well, see if I do that, I'll destroy my WebEx connection. In a DHCP discover message, there is actually DHCP payload information. I'm going to try it anyway. If these guys get disconnected, well, oh well. We'll get them reconnected. All right. So let me go to my Wireshark tool here. I guess this will work. All right. And actually, first let me see if I even have any DHCP messages, because then I don't have to break anything. So I'm going to do a search on a protocol. Now, DHCP happens to use port 67 and 68. So I could do a filter on apply filter selected, and I could do 67. Or I could do 68 to see, and I don't have any, let's do also DST port. So I didn't capture any DHCP messages. So let's go ahead and start our capture. And I'll go to my command prompt. It's still not clearing the filters. Why didn't it clear my filter? There we go. All right, so I'm capturing data. I'm going to come into my command prompt. All right. First of all, I'm going to do an IP config. And what I'm looking for here is I'm just looking for the current address that I have assigned. And I've got, looks like on my wireless, I've got this right here, 192.168.18.126. So I'm going to do an IP config, release, and a renew. Yeah, they're gone. They'll be back though. I lost all my GNS3 stuff because it released all my addresses from there too, but we'll get those guys back. And I'll do a quick renew. And as long as I don't get a message popping up saying, hey, I can't get to WebEx anymore. All right, so I've gone through the process. Let's see here. Should still be online. I don't see my microphone moving anymore there. WebEx hasn't freaked out just yet. See if we are connected. See, it didn't renew my lease. So let me disconnect from there and I'll just reconnect to a different wireless network here. Okay. So got to make sure we get on our WebEx here. There we go. Now we're back. Well, let's see. Brandon is there. I can see him talking. We're back, and now let's go ahead and stop our capture. And I want to go ahead and sort by protocol, source port. And I'm going to apply a filter selected based on port number 67. Let's see if we have 68. Interesting. All right, then let's go ahead and apply a filter based on protocol. Surely I must have captured some DHCP messages there. Let's see. It would be UDP. Well, let's just sort by this way. A lot of ARP. There's some DHCP. I wonder why it didn't find it based on port number. That's really strange. You look at a DHCP message, you will see, in fact, that it does use port 67 and 68. But it does use 67 and 68 based on, yeah, it should have still found those, but oh well, no big deal. But here's the point that I was trying to make. Yes, there is a MAC address in the frame. There is a MAC address in the frame, but when a DHCP server is responding to a discover message, in fact, let me grab a DHCP discover here. When a DHCP server is responding to a discover message, it's actually looking at what's contained in the bootstrap protocol to assign the appropriate address. So it's actually this field right here that it's looking at, client MAC address field. It's not looking at the actual data link layer frame. So if I'm trying to spoof a bunch of DHCP discovers, I don't even have to change my physical frame. I don't have to change my physical MAC address. All I have to do is spoof that field with a bunch of different MAC addresses, and the DHCP server will think that these are coming from unique clients. Okay? So while you think that port security might protect you against this kind of attack, it doesn't. All right? Which is why we have to rely on other mechanisms to protect our topology. Okay? And that's, of course, what we're going to talk about right now. DHCP is a broadcast-based protocol, which means it's highly susceptible to attack because anybody can respond to DHCP discovers, and anybody can generate a DHCP discover. The bottom line there on the slide, you see DORA, D-O-R-A. DHCP discover, DHCP offer, DHCP request, DHCP acknowledgement. So we can implement a feature in the switch. This would be something that you would enable on a switch called Dhcp Snooping. All right? All this slide is trying to show you is essentially what is DHCP spoofing. Basically, it's just a rogue device out on the network sending out DHCP offers. Clients send out a discover. Some rogue device out there, whether it's intentional or not, sends out a DHCP offer message. The client is then just going to accept the first offer it gets. I've seen this a lot, by the way, guys. Somebody goes and buys a little Linksys wireless router because they want to get wireless. They're not allowed to join the corporate wireless network, so they just plug it into the switch and they want to get wireless, but then that becomes a router on the network, starts handing out DHCP. I've actually literally seen that a few times. Okay? It's not that the legitimate DHCP server still can't respond to requests. It still can. It just responds too late. And by the time it responds to a DHCP discover, the client has already accepted a discover from another device. Now, that doesn't necessarily mean it's malicious. Somebody could actually also send in or put in a rogue DHCP server for the purposes of injecting false information to the client's configuration. I want to make you use the wrong IP address for your gateway. I want to make you use the wrong IP address for your DNS for the purposes of influencing how the traffic flows from that client. Okay? DHCP Starvation Attack, which we just talked about, somebody sending in a whole bunch of DHCP discover messages with a spoofed MAC address. And when we say spoofed MAC address in this case, we are talking about the DHCP payload being spoofed, not the actual frame itself. So port security wouldn't necessarily protect us in this case. How do we protect against both of these? Well, we protect against both of these by implementing a feature in our network called Dhcp Snooping. What Dhcp Snooping allows you to do is identify what we call trusted and untrusted ports on the network. By default, when you enable Dhcp Snooping in your network, all the ports are untrusted. What that means is those ports cannot source server-based messages. They can't send offers, and they can't send acknowledgments. Untrusted ports can still send in discovers and requests, but an untrusted port cannot send offers or acknowledgments. So if I go into my switch here, and I configure Dhcp Snooping on this switch, all the ports become untrusted by default. Which means if you've got an attacker here sending in offer messages, those offers are going to get blocked at the port level because the port is no longer trusted. Make sense? So the switch builds, and actually that does a little bit more. It also builds something called a Dhcp Snooping binding database, where the switch is actually monitoring all the transactions that occur between two devices. Let's say you've got a legitimate Dhcp server here, and you've got a client here sending in a discover. That discover goes through the network, comes over to the client, the server. The server sends an offer message because that port is trusted. I'll show you how to configure a port as trusted. That server sends in an offer message. That offer comes all the way back, because these ports are trusted, to the client. And that whole process, that DORA process, is being monitored by the switch. And the switch is actually building a database. MAC address, IP address, port number, VLAN, everything is being mapped to that specific port. So the switch knows this client requested an address, this client received this address, this client is in this VLAN, this client is on this port. That's called a binding database. All right, that binding database is actually pretty important for the next protection mechanism that we're going to talk about, which is dynamic Arp Inspection. The other thing that, yeah, go ahead.
So those green and red circles, are those just representing the trusted and untrusted ports?
Yes.
So you wouldn't want trusted ports on any of the, I guess, the
Core switches.
right.
You would actually most likely not even be running Dhcp Snooping on these switches. If the only place you would want to run Dhcp Snooping is any switch that has the potential of having an attacker connect to it. Right? So your core and your distribution switches, usually those are in your data center. They're protected. People can't just plug in and put in a rogue DHCP server. But your access layer switches, yes. And you might decide to run it on this switch or not. It's up to you. We're assuming that your DHCP server is probably going to be connected to some sort of distribution layer switch anyway. But you don't necessarily have to run DHCP snooping across the board. Just on the switches that might be affected by either a rogue DHCP server or a client that's doing some sort of starvation attack. All right? So the reason we don't have, yes, if you did have DHCP snooping here and here, you'd essentially make all the ports trusted, which is kind of like, well, there's really no point in running it at that point. Does that make sense?
Yes.
All right. How do we configure this? It's actually very simple. It's so simple that you should be running it. All right? This is enabled on a per VLAN basis. So you can choose to enable it on, maybe you don't want to run it on your voice VLAN, but you want to run it on your client VLANs. All right. The feature is implemented in software on something called the route processor. And all DHCP messages for the VLANs are intercepted in the route processor and the PFC, the forwarding engine, and then they're directed to the route processor for processing. Why is that particularly important? It does require CPUs on the device. The device is doing higher level analysis of these DHCP packets, so it is going to require additional processing. All right, you're going to rate limit untrusted ports per second. This is Cisco's recommended value. I've never understood that value, 100 packets per second. That seems like a high number for DHCP snooping, but that's what they typically recommend. And then anything that goes over that rate, error disables. The rate limiting feature is what you would want to implement so that you're reducing the likelihood of a starvation attack. Snooping by itself doesn't really prevent a starvation attack. It prevents rogue DHCP servers. The rate limiting piece is what allows us to prevent a starvation attack because we're limiting the number of DHCP packets that can be generated on a port over a period of time. All right, here's the config. Enable the feature globally on the switch. Doesn't actually do anything by itself. That just simply enables the switch to start building its databases. Oops. Let's go with yellow here. Enables the switch to start building its databases. So I come in and I go into my switch here. Lost all my connections. GNS3 is definitely sucking up my memory. There's no doubt about that. All right, so I can come into ASW1. Okay, I get it now. I lost all my connections. Thank you. Any more? Which one was my ASW1? Right here. So I can come into my ASW1. Did it actually kill my GNS3? Seems that way. Let me clear all these out. Let's clear. Yeah. I was going to try and close them all. It's grayed out though for some reason. Oh, there it goes. Okay. All right, let's go back to our GNS3 and hopefully the GNS3 didn't crash. Ah, it did. Okay. So, as we said before the break, IP DHCP snooping is what's going to enable the feature globally on the switch, although it's still not technically running in this case because you do have to apply it on a per VLAN basis. So the second command is what actually enables the feature on the VLAN itself, IP DHCP snooping, and then you would specify that on your VLAN. Go into the interfaces. Oh, by the way, be very careful with this right here, because as soon as you execute those two commands, DHCP snooping is enabled globally on that switch for that VLAN, which means all DHCP server messages are untrusted by default. So if your DHCP server happens to be connected to this switch, or if you have some uplink switches that go to the core of the distribution layer, you got to be careful because now you're blocking DHCP offer messages and you're blocking DHCP acknowledgement messages. Any interface that requires the trust, you go into the interface and you specify IP DHCP snooping trust. You would apply this to any of your uplink ports, that go to so for example, on the previous diagram, I would enable the trust command on this particular interface here, this interface, this interface, this interface. Untrusted is automatically configured on all the interfaces, so I don't have to make a port untrusted, but I would make all my uplink ports trusted. If I did decide to run Dhcp Snooping here, I'd of course want to make that port trusted as well, so that the port can send and receive offers and acknowledgments. Untrusted ports are allowed to source DHCP client requests always, which is the discover and the request. But the offers and the acknowledgments are only server-based messages that are allowed only on trusted ports. All right? So you go into the interface. You go into the interface where you want to trust the information, put in IP DHCP Snooping Trust. Any of the untrusted interfaces, one of the things that you may additionally want to do, so let's say our server is plugged into port 1, but we have a standard DHCP client plugged into port 10, I may choose to rate limit that port to a specific number of packets per second. I read in a document at some point or another, I can't remember which one, but that Cisco recommends a rate of 100 packets per second. That seems really high to me. It seems really high because I mean, you're talking about not 100 packets per second. You're talking about 100 DHCP packets per second. That'd be pretty significant in my opinion. I don't think a client should ever have to generate that many packets per second to process DHCP. So you might decide to maybe drop that number down a little bit depending on your environment. All right. So this port is now untrusted, port 10. Which means we're going to block any DHCP offer messages that come into this port. We're going to block any DHCP acknowledgments that come into this port, which prevents our DHCP spoofing attacks, where we're actually putting in a rogue DHCP server. In addition, we're rate limiting the DHCP traffic, which is also going to prevent our DHCP starvation attack. Okay? That's the entire config, guys. That's it. On your trusted ports, you just put trust. You can also rate limit your trusted ports as well if you choose to, but it's usually not done. We usually just let an unlimited amount of data flow through that interface because that server is most likely going to be responding to lots and lots of different DHCP requests. And if you do a show IP DHCP snooping, you can see that port 010 is untrusted, and it's rate limited to 100 packets per second. Port 01 is trusted, and it's not rate limited. If you want to see your binding database, so as traffic goes back and forth across the interface, as DHCP discovers and offers go flying back and forth, that DHCP snooping binding database gets constructed. This is what it looks like. There's actually no entries in here, but I wanted you to see the information that DHCP is capturing for the process. The MAC address, that would be the MAC address of the client that's requesting the DHCP information. The IP address, which would be the IP address that was offered to the client, and not only offered but also accepted by the client. So there's your MAC to IP binding, the amount of lease time left, the type, whether it's a static entry or a dynamic entry, the VLAN that the client's a member of, and the physical port that the client's a member of. All of these fields are relatively important to track, especially if you're going to use this database for other functions like dynamic Arp Inspection, which we will actually do. We'll actually see these used for dynamic, this database used for dynamic Arp Inspection as well. Should I add this to our best practice configuration? Yeah, I think so. I think DHCP snooping is definitely something that you would most likely want to run on not all of your switches, but certainly some of your switches. So we're going to go ahead and add some text to our best practice configuration document, which is right here. All right. So these would be global config commands, IP DHCP snooping. and then IP DHCP Snooping VLAN ID. All right. And then for host ports, well, this is, yeah, on a host port, I would do IP DHCP Snooping Trust. Enable this on host ports, or technically could be trunk ports as well if you're running a VMware server with a DHCP, but enable this on host ports that connect to a valid DHCP server. And we would also do IP DHCP Snooping, and we could do our rate limiting right here, limit rate to the number of packets per second, limit rate. I'm actually probably not going to say 100. Even though Cisco recommends 100, I would even say 20 packets per second would be sufficient. There's really no reason that a client should be sending out, 100 DHCP discover messages in a second. Even 20 is kind of high, really, if you think about it. So, but I will put 20 because, well, that's fine. Limits the amount of packets per second, well, let's say DHCP packets per second, a port is allowed to receive. All right. Is there anything I would do under the trunk port in this case? Do I need to apply any kind of DHCP snooping commands to my trunk ports? Probably what? Would. Sorry?
You say wouldn't.
You wouldn't apply it? You would, right? I know he said wouldn't. I'm correcting him. I'm saying would.
Not a limit rate, maybe not.
Yes, not rate limiting, correct. But I might have to do IP DHCP Snooping Trust, right, for my uplink ports to the, well, let me see. How do I want to word this? In the direction of the DHCP server, usually which is kind of to my server farm or the distribution layer. Does that make sense? If you read that later, you'll understand what that means, right? I'm going to enable DHCP Snooping Trust on the uplink ports. I'm going to only do that on the switches that I'm obviously running DHCP snooping on, of course. But this is a mechanism that allows those DHCP offer messages and discover message, or excuse me, offer and acknowledgement messages to go through those ports. Yeah, that's it for that, DHCP snooping, pretty straightforward. Now, what happens if I run into a situation where I don't have a port that's even running DHCP? Right? Do I concern myself with whether I trust or untrust that port? I really don't care, do I? If I've got a router, for example, if I've got a router connected to a switch port, and it's not a trunk, but it is a host port or whatever, it could be a trunk as well, do I really care whether or not I'm trusting that port or not? As long as the router's not generating DHCP offers and acknowledgments, I don't care. Although you could be running DHCP on a router. In that case, you'd want to make that a trusted port. But I don't really care if there is no reason the client is running DHCP. Like, for example, a VMware server. That's probably a better example, right? If I have a port that's connected to a VMware server, there's my VMware server, there's my switch. As long as I'm not running DHCP on that VMware server, I don't really care about whether or not that port is trusted or not. Or do I?
I think you would, because even with VMware, it's a trunk that you configure to that, right?
Well, whether it's a trunk or not doesn't really matter with regard to whether it's trusted or not, right? All you have to consider is, what am I trying to protect myself against? I'm trying to protect myself against a rogue DHCP server, which hopefully that wouldn't happen on your VMware server, especially if you're not running DHCP on that box. And I'm also trying to protect myself from starvation attacks. So the reality is you probably would configure it on that interface, because if somebody compromises your VMware server, they could use that server to launch a denial of service attack against your network, or they could actually install a rogue DHCP service on one of those servers, and then they could start acting as a DHCP server. So you always have to consider, not only, just because you're not running DHCP on a port doesn't mean you don't necessarily still want to protect yourself. Somebody could also simply unplug the cable and plug something in and start doing something on the port that way too. Now, the benefit to DHCP snooping is that by default, if you run DHCP snooping on a switch, the port's automatically untrusted. So unless you explicitly trust the port, it's going to automatically be untrusted anyway. So you're kind of protected in that sense. Does that make sense?
But just because you turn it on, if you don't put the rate limit, it's not going to...
You're not going to protect against starvation attacks, because by default, there is no rate limit. There's only a rate limit here because we set it. But by default, there is no rate limit for the number of packets per second. Another protocol that's highly susceptible to attack is ARP, the Address Resolution Protocol. Basically, you've got a client here that wants to talk to Barney. Fred wants to talk to Barney. Fred says, well, before I can talk to Barney, I need to know Barney's MAC address. So it sends out an Arp request. Arp requests are basically their own layer 3 packet. If I go into my Wireshark here and I pull up an Arp request, oops, let me go by protocol here. You can see that an Arp request is a very basic packet type. You've got your destination MAC is a broadcast. Your source MAC is whoever's sending the Arp request. The type field is hex 0806. So Arp is not encapsulated inside of IP. It's actually carried over as its own layer 2 or layer 3 protocol, excuse me. It's the actual request that contains the information relevant to the actual request itself. This particular MAC address with this IP address is trying to find 18.132's 18.132's MAC address. Why is this vulnerable to attack? Within a subnet, of course. Why is this vulnerable to attack?
Everybody gets it.
Everybody in the VLAN gets it. Everybody in the network gets it because the switch floods that information. And the client or whoever gets this, they're technically not supposed to respond if their address isn't 18.132. But I mean, an attacker doesn't care about what they're technically supposed to do or not supposed to do. So they're going to go ahead and send in a response. They're going to say, okay, I'm going to respond on behalf of this client, and I'm going to give him my MAC address. That's called ARP poisoning. I'm going to poison his ARP cache with my MAC address so that I can start capturing information about that, or data that's supposed to go to that legitimate client. Okay? You could also see potentially a denial of service attack with ARP, just sending a bunch of ARP requests, flooding the network with a whole bunch of ARP information so that people couldn't use the network. But most of the time, you're mostly concerned about spoofing attacks or ARP poisoning attacks, where you're trying to spoof somebody's MAC address or you're actually trying to act on behalf of somebody else. So we want to protect ourselves against this type of attack as well. Okay? Here's an ARP poisoning attack. This client says, I need the MAC address for 10.0.1.1. Okay? This is the source IP. This is the MAC of my client. The switch is going to add MAC AAAA to the port, and then that ARP request gets flooded out. Okay? So I flood that out. I flood that out. Now what happens is the router, which is 10.0.1.1, responds with its MAC address, totally legitimate MAC address, sends that in. There's an IP to MAC binding here. That's very important to understand. The switch is not really looking at that IP to MAC binding to verify that it's correct. It's just going to respond or forward that ARP request back to the client, and then the client is going to update the table, the ARP cache, with the appropriate information. All right, so this is the legitimate information. The attacker says, I want to capture all that traffic going to 10.0.1.1 because that's the gateway. That means I get all that client's internet traffic, or not internet, just anything outside of the subnet. So I'm going to send a subsequent gratuitous ARP. Gratuitous simply means I'm sending out an ARP that wasn't officially requested. I'm going to send a gratuitous ARP, and I'm going to not only overwrite the MAC address of the gateway, I'm going to overwrite the MAC address of the original host that requested the information. I'm going to send this gratuitous ARP over to this client, and I'm going to send this gratuitous ARP over to this guy, hence the term man in the middle, because basically I'm telling both of these guys, hey, if you want to talk to that MAC address, you need to send the traffic, or if you want to talk to that IP address, send the traffic to MAC BBBB, which is the attacker's actual MAC address. The reason why the switch may or may not understand what's happening is because it's not the actual frame header that the clients look at to update their ARP caches. Just like DHCP, it's the payload information that we look at. This source MAC doesn't have to match the sender's MAC or the target MAC in this field. I can poison ARP without actually changing my physical MAC address. Does that make sense? The switch makes forwarding decisions based on the physical MAC. Clients make decisions based on the MAC address that was described in the ARP payload. Now, that's not to say that this attacker doesn't want its MAC address to show up on that port, but it would anyway, because that's the actual physical MAC address that it's using. So when I'm doing the poisoning, I'm not poisoning the actual frame header information, which means port security doesn't protect against this type of attack either. I'm not poisoning the actual frame header information, I'm poisoning the ARP payload information. So port security would not protect against this type of an attack. You guys understand? I mean, I think you guys understood basically before this discussion what an ARP poisoning attack is in general, right? But you may not have been aware that it's not the layer 2 data that I'm modifying, it's the layer 3 data that I'm modifying, which means port security doesn't protect against it. They look like normal frames to the switch, and they actually look like legitimate frames to the switch. So now this client, when it wants to talk to 10.0.1.1, it's going to send its traffic to BBBB. Because BBBB is written to this interface, the switch is going to forward that information down to that port. This PC can copy the data, can modify the data, can do whatever it wants. And because it knows the real MAC address of the router and the real IP address, it can actually forward a legitimate frame to CCCC, and that will go to the router. The router thinks it's just getting a regular frame. It's going to send it out to the internet. The traffic's going to come back. Router C thinks that the MAC address for 10.0.1.2 is BBBB, so when it builds its layer 2 frame, it's going to send it to BBBB. That'll come down here, and then the PC can then forward that information over to PC1. And now I've inserted myself into the conversation, and neither host A or the router are even aware that that's happening. Does that make sense? Well, there must be a way for us to protect against this. I'm glad you asked. It's called Dynamic Arp Inspection. Dynamic Arp Inspection. First of all, in order to run Dynamic Arp Inspection, you also have to be running Dhcp Snooping. Dynamic Arp Inspection does not work without Dhcp Snooping. Okay? So what happens in this case is we go through and we validate all of the ARP packets in the network. With Dynamic ARP Inspection, we validate IP to MAC address bindings in the Dhcp Snooping database. If you remember on our Dhcp Snooping database, We had MAC address to IP address to lease to type to VLAN to interface bindings. So I was actually binding the MAC address of the host to the IP address that that host is supposed to have. By inspecting that database, essentially what will happen is I'll be able to validate or invalidate ARP responses or ARP replies based on that information. Because we verify every single one of the ARP messages against this IP to MAC binding database that gets stored because of DHCP snooping. All of the invalid ARP packets get dropped. So here's the scenario. Router here, MAC address 2234, okay? Gateway is 10.0.1.1, so obviously this traffic needs to go to 2234. All right, now let's say my attacker machine connects to the network. In order for my attacker machine to be able to communicate over the network, it's going to have to go through the DHCP process to get an IP address. Agreed? And in that DHCP process, I'm looking at the MAC address of the client, the physical MAC address of the client, and I'm monitoring this transaction with the DHCP server, so I am binding this MAC address to this interface to whatever IP this attacker got in the DHCP process. You might think, well, what if I don't want to do that? What if I just want to use static IP address on the attacker? Well, if I use a static IP address on the attacker, what's going to happen? I'm not going to have a binding in the database, which means I'm still not going to be able to validate the ARP messages from that client. No binding in the database doesn't mean we simply allow it to pass. You either have to create a static entry in the database, or you have to turn on trust on that port to trust all of the ARP packets that are coming from that port. So the router or the attacker here says the gate with a MAC address for 10.0.1.1 is 2345. Well, the switch is going to go, wait a minute, no it's not, because I have a binding in my database that says the MAC address for 10.0.1.1 is 2234, and that's on this port. So it can't be 2345, and it can't be on that port. So that basically then blocks that attacker from sending that poisoned ARP into the network. Would I have a binding for that router in the database, though? Most likely not. You guys agree with that? Routers don't usually run DHCP on the interface. They're usually running static IP addresses. So I wouldn't necessarily have a binding in the database for that. What I would have to do is I'd have to go create a static binding in that database. And you can actually create static entries in your database. Okay? You guys understand the general principle here, right? I'm looking at the DHCP snooping database. I'm matching up all the characteristics of the ARP packet, whether it's a response or a request, and I'm either allowing or disallowing that ARP packet based on that response or request. How do we configure this? It's very simple. One command, IP Arp Inspection, VLAN X. Global command that turns on dynamic ARP inspection on the VLAN. By default, every port in that VLAN on that switch is now untrusted. Every port in that VLAN on that switch becomes untrusted by default. Basically, what does it mean when you're running dynamic ARP inspection and a port is untrusted? It means that all of the ARP packets are getting inspected. And if there isn't a binding in the database that correlates to that ARP packet, the packet gets dropped. It's that simple. So before you do this, you need to make sure that your binding database is populated. If your binding database is not populated, then ARP's not going to work and nobody's going to be able to communicate. This one requires a little bit more planning before you actually turn it on. All right? Have you guys ever used ARP inspection? Yeah, it's not that common, but it is useful. And actually, I would add it as a best practice standard, but you have to be very careful with it because it does rely on DHCP snooping. So DHCP snooping needs to be enabled for the VLAN, And all the ports that don't run DHCP, you need to make sure you add static bindings in the database, or else they won't be able to send or receive ARP requests on those particular ports. The other option you could do is just simply go into the port and make it trusted. So in this example here, maybe I don't want to add a static binding for this client. I could just make this a trusted port, and all ARP messages are allowed to go in and out of that port without being inspected. Better option would be to actually create the binding, though, so that you can do it. So you can do the inspection is what I meant to say. All right?
But port security will stop this as well, right?
No, it will not.
So
Why wouldn't it?
the spoofing of the address, if you've already got
MAC address spoofing is not the same as ARP poisoning. MAC address spoofing is not the same as ARP poisoning. MAC address spoofing is where you're actually changing your layer 2 frame information. You're changing the MAC address of your frame header. In ARP poisoning, you're not modifying necessarily the frame header, you're modifying the ARP information. Well, port security doesn't look at ARP payload information, it looks at the frame. See what I'm saying?
Yeah.
So I can poison ARP information by sending out a gratuitous ARP and overriding this information. This MAC address doesn't have to match what's in the ARP payload in order for it to be evaluated. Because what happens is, let's say I do send out a poison request. So it's a broadcast, which means everybody has to open it. All right. I have a target IP and a target MAC, so that's the victim. Target IP and the target MAC would be the victim if this was a response, not a request. But the target MAC and the target IP would be the victim, and the sender's MAC and sender IP might be the gateway, the default gateway, then the sender's MAC could be my MAC, which would match this MAC address on the frame as well. But if I'm trying to poison maybe information to different MACs, it wouldn't matter, because there's no correlation, direct correlation between the frame header and the ARP payload. Right? Now, when you're using dynamic ARP inspection, it looks at both of them. It looks at the frame header and the payload, and it makes sure that everything is legitimate. There's no reason you should be sending an ARP response with a different MAC address than your physical MAC. So we're not going to allow that. Does that make sense? The reason why port security wouldn't block it is because port security only looks at the data link layer. It doesn't look at the network layer. All right? That's different than MAC address spoofing. In MAC spoofing, you're just changing your frames to look like they're coming from somebody else. In that case, you could be protected. So if I added this, I would say, okay, in global mode, I would do IP ARP inspection, right? And we could do it on a per VLAN basis. You could do a range of VLANs. IP ARP inspection, VLAN ID, enables the IP ARP inspection, enables IP ARP inspection on the VLAN. And it requires DHCP snooping first. All right, because ARP inspection relies on that DHCP snooping database to function. On my host ports, I might, well, there isn't a whole lot I really do on my host ports, right? I might do IP ARP inspection trust. So right here, IP ARP inspection trust. If it's a port that I don't want to be inspected, only enable on ports without DHCP bindings or ports you explicitly trust, meaning no inspection. All right? You would do this on trunk ports as well, by the way, because trunk ports pass traffic as well, and there's binding databases related to the trunk port. So I could go ahead and copy this and also enable this on the trunk port. Trunk ports are automatically untrusted as well. So you would want to do a trust on your trunk ports. Usually you almost always do a trust on your trunk ports. It depends on whether the DHCP traffic is passing through that trunk port or not. All right. That's really the only options that you have. You can do rate limiting. So this would prevent some sort of denial of service attack on a particular port. In this case, we're rate limiting ARP packets to 20 packets per second. That would be typically something that you would do on a host port. You would do the IP Arp Inspection limit rate. We'll do 20. Limits the amount of ARP, I'll just do this. ARP packets per second a port is allowed to process. Okay? You typically wouldn't rate limit your trunk ports, you'd only rate limit the host ports. So we can see here port 1 is trusted. We're not doing any rate limiting. Port 2 is untrusted. Untrusted basically means we're going to do inspection. Trusted means we're not going to do inspection. All right. So that concludes that lesson, which is all of our layer 2 protection mechanisms. Let's take a look at what we're going to see in the next chapter. I know we're getting close to our cutoff time, but let's see what we got in the next chapter here.